So I am recording this retroactively. So I'm just kind of recording a little introduction real quick. If we go to maybe exam 3 and look at this, I just want to talk about like the objective of this real quick. We are going to go through and talk about this Lewis relationship and talk about relative humidity, and then we're going to talk about adiabatic saturation temperature. And all this A1 is basically setting us up to solve a problem in B1. And this problem in B1 is it's this right here. So we have a cooling tower, and this cooling tower is having water that's hot being put in, and air that is cold being put in, and it is trying to lower the temperature. So, yeah, that's just kind of a quick, yeah, I guess kind of almost a briefing on, like, what we're going to be doing. Am I still recording? Yeah. So that's just kind of a briefing on what we're going to be doing. We're going to solve through all these parts, and hopefully you'll learn something. So, I'm Ben, and I'm looking forward to teaching you all. Thank you. Hey, everybody. So this is part A1. And the goal of what we're trying to do right now is we are trying to explain the Lewis relation. So I'll just go ahead and take a screen cap of that and go ahead and just put it in the document. Right there, it looks pretty good. So this is the Lewis relationship. And I'll get to the Lewis relationship in a minute, but why don't I go over some relationships that we've already derived. So first things first, last exam, I derived this. That the Sherwood number is equal to some constants times the Reynolds number times the Schmidt number. And this describes mass transfer, right? And the Sherwood number we defined as the mass transfer coefficient times the characteristic length all over the diffusion coefficient from the two materials. And the Schmidt number, which is important here, is this dynamic viscosity right here. All over once again, a diffusion coefficient. Now, if we were to do a similar sort of heat transfer experiment for the similar to the experiment we did last time, we would find a relationship with this Nusselt number. The Nusselt number is defined as the heat transfer coefficient times the characteristic length over the thermal diffusivity. And we would find that with some constants, and then we would relate that to actually the Reynolds number. And then we would also relate that to the Prandtl number, or the Prandtl number, which is a dynamic viscosity over the thermal diffusivity. And the thermal diffusivity is short for this conductivity over rho Cp, or the density times the specific heat. And this is pretty important. These two relationships are going to let us do some pretty important stuff. So why don't I just go ahead and talk about the Lewis relation. So the Lewis relationship is the Schmidt number over Prandtl number. Awesome. Video over. Just kidding. Let me go ahead and explain it a little bit more. So the Schmidt number is going to be this characteristic viscosity, which I'll just go ahead and copy. Actually, I don't even have to do that. I can use the select tool. I'm just trying to get this to go through a little bit faster. And we can select that and put that down there. And then, we see that the Prandtl number is, that right there. So you look at these and you can see right off the bat, the dynamic viscosities cancel out. So we're just left with the diffusion coefficient from the two components involved over this thermal diffusivity, which I'll just go ahead and actually write that in. So we'll write down what those values actually represent. This thermal conductivity and the density and the specific heat capacity. So if we were to rearrange this, we would actually find that this whole value, of course, is equal to the Lewis number. But if we were to go in and plug in all of these constants for a humid air-water system. So let me write that down. A humid air. So for humid air, all these things are equal to 1. And basically what that's going to let us say is that the diffusion coefficient over mass transfer coefficient is going to be, I'm writing this in reverse. Sorry, let me go back for just a second. Really, we want to be able to say that the mass transfer coefficient, or the thermal diffusivity, there's a lot of K's in here. It's a little bit hard to follow sometimes. Over the diffusion coefficient from A to B is going to equal the density times the specific heat capacity. So that's pretty important to what we're going to end up doing later. But let me box that in, and I'll make sure I save the document. And let's go ahead and let's find the relationship between the Sherwood number and the Nusselt number. So the Sherwood number over the Nusselt number, well, what do those two things equal? Well, the Sherwood number is just going to be the mass transfer coefficient times the characteristic length all over something, all over the diffusivity. And then the Nusselt number, we'll go ahead and copy paste that down, and we'll see that the Nusselt number is that. So what cancels out here? Well, we can see this characteristic length cancels out, and when we go ahead and solve that all out, we can write it all down. We will see that, we will see that the mass transfer coefficient times the thermal diffusivity, so K and K, all over the diffusion coefficient times the heat transfer coefficient is going to be equivalent to, well, Sherwood number over the Nusselt number. If we were to take these two things and divide them, we would see that that would equal the Lewis number, which in this case for humid air, once again, is going to be 1. So we'd see that equals 1 as well. Now, because that equals 1, we can move around these terms over there, and we could actually create the relationship once again that mass transfer coefficient times the diffusivity is going to equal the okay, so I need to sorry, I wrote it a little bit wrong. I mixed up my it appears I mixed up my thermal diffusivity with my with my mass transfer coefficient. We would get the heat transfer coefficient over Kc, and we know from up here, once again, this box, we know that that is also going to be equivalent to the density times the specific heat capacity. So, these two relationships are for humid air using the Lewis relationship. So that is basically a summary of what the Lewis relationship is. The important parts for what we're going to go on to do for this is going to be that the Lewis relationship means we can relate density and specific heat capacity to mass and heat diffusivity. So for a humid air where there's a lot of water dissolved in the air, or not dissolved, I guess that's not the right word, but where there's water diffusing into the air. That these two relationships describe the system. So with that in mind, I'll go ahead and move on to the next part. Thank you. Okay, so for this next part, I want to explain how the Lewis relationship is used as a part of an energy balance to determine the relative humidity from wet and dry bulb temperatures. So, let's just explain this whole dry and wet bulb thing real quick. So let's say you have two thermometers, right? One has a dry bulb, hence the dry bulb temperature. One has a wet bulb, hence the wet bulb temperature. Now, if you have these two things sitting in a room, are the temperatures going to be the same, or are they going to be different? Well, if that room were in a vacuum, they would be the same, because, there wouldn't really be heat very well, but that's not even relevant. When you start to move this wet bulb thermometer around and start to expose it to a lot of air, some of this water is going to evaporate into the air. And when it does that, it's going to take heat with it, and so the temperature that the wet bulb thermometer reads is going to go down. So there would be a difference between the dry bulb's temperature and the wet bulb's temperature. Well, once this difference has started, am I recording? Yeah, I'm recording. I'm sorry, I just got caught up in it. Anyway, there's going to be a difference between this dry and wet bulb, and because of the water from the bulb evaporating into the air. Now, if the air is totally saturated, the humidity is 100%, then this wet bulb none of the air is going to evaporate, and the temperature is going to be the same. But if the air is really dry, then the water is going to evaporate rather quickly, and there's going to be a pretty significant temperature difference. So relative humidity can be defined as the partial pressure of water in the air divided by the saturation pressure of water at a certain temperature. And this bottom part we can find from an Antoine. The bottom part we can find from an Anton equation, right? So that's all good, but this top part is a little bit more difficult. So how are we going to figure out this top part? Well, let's see. We need to set up some kind of energy balance, right? So why don't we set up a balance of the heat energy it takes to evaporate. We'll put evap over there, and we'll set that equal to the amount of energy that it takes to maybe not evaporate, but the amount of heat from air, because heat from air is causing the evaporation in this case. So let's go ahead and set these things equal to each other, and we'll solve it. So first off, let's set up the mass transfer. So the mass transfer coefficient times the difference in concentration between the surface and the air. Now we want this number to be positive, so we should put the one with the higher concentration, the concentration in the surface, minus the concentration in the air. Now the heat from the air, that would just be the heat transfer coefficient times the temperature difference, but we want the temperature difference to be positive, and the temperature in the air is going to be higher than the temperature at the surface. So that's kind of how we got there. Now, real quick, this is in mass transfer. This is in heat transfer. We want them both to be in heat transfer. So let's multiply this by the enthalpy of vaporization, which this is in joules per mole. So this is going to show us, this is going to let us go from moles per meter squared per second to joules per meter squared per second. So this is like a heat diffusion, essentially, right? So, that's just something that is important to keep in mind, and that's going to let us work some stuff out. So there's a couple things I want to do here. First, you see I brought in this relationship we found last time, that the heat transfer coefficient over the mass transfer coefficient is equal to the volumetric heat capacity. And you see we could apply that here, right? Because we've got a Kc, we got an H, we could divide that over, and so we could apply this relationship. But another thing we can apply is that concentration is equivalent to, according to the ideal gas law, of the pressure over RT, the gas constant times the temperature. Now, we also know that density is m over v, right, mass over volume, and that can also be related to the ideal gas equation. So we're going to use that to simplify this and to bring in the partial pressure of water. So I'll just start rewriting like the simplified form of this equation. So we bring down the specific heat capacity. Now then we're going to turn these concentrations into partial pressures. So the concentration at the surface is going to turn into partial pressure of the surface, partial pressure of water at the surface, because this is concentration of water, minus the partial pressure of water far from the surface in the air. So infinity, infinite distance. That's kind of a way to think about it. And then we're, of course, going to divide that by the gas constant times the temperature. Now, over here, we divided over this mass transfer coefficient to the H. We got a rho Cp. I'll just write that in for a second, but we're going to change this density into something else. So I'll go ahead and grab this density. And, let me write in the temperature part of it, too. And then, of course, we're going to keep this temperature difference over here because we're already measuring the temperatures pretty easily, so that's pretty important to keep in there. So we can just go ahead and select this and delete it. And what would density turn into? Well, we found that over here. So this is the total density, by the way. So this would be the total pressure, big total pressure, I guess. I don't know why it's so big, times the gas constant times the temperature. So yeah, you can see the gas constants and the temperatures cancel out here. And we are given an equation that gives us the partial pressure of water in the air from the temperature difference, the specific heat capacity, which is just from literature, right? The total pressure, which we could find with like a barometer, and the specific heat capacity, which is from, or the enthalpy of vaporization, which that is just from, that's from literature as well. So basically, just using like the temperatures measured by by the thermometers, we can find the relative humidity. So that is how the Lewis relationship is used as a part of an energy balance to determine the relative humidity from wet and dry bulb temperatures. Thanks. So for part 3 of this video, I'm going to explain the relationship between adiabatic saturation temperature and the wet bulb temperature, which is what we just did. And I'm really going to show how these equations are very similar, or basically the same equation, just kind of reflecting different sort of conditions almost. So let's talk about an adiabatic saturation situation. So we have a pipe with air flowing through it and water in the pipe. Now this air comes in at a certain mass, and it's adiabatic, by the way, and adiabatic means there's no heat transfer in and out. So that's almost saying there's like a lot of insulation. There's really effective insulation in here. So it enters at a certain temperature, or at least the water does, and there's a pressure of water when it enters the cylinder, and then when it comes back out, there is the same mass of air entered, or at least mass of air in the sense of like dry air. If you say like, oh, water vapor is joining the air, if you consider the water vapor a part of the air because it's evaporating, then yeah, it would be a little bit different. But the actual amount of like bone dry air is the same coming out, the mass of it. And at the end, because this pipe is infinitely long, that means that the saturation pressure of the water, or the pressure, the partial pressure of water in the air is actually going to be the saturation pressure at the end for whatever temperature the system is. So yeah, that's the TW. So yeah, you'll see like a couple of variables similar to what we've talked about up in this part 2 with the wet bulb temperature. So this was explained in the last part. Yeah, so as soon as it says adiabatic, you have to think about making an energy balance. So let's set up some equation with like an enthalpy, or maybe I'll put it as an H. So H for enthalpy in, and then we'll set up an enthalpy out as well. So let's start out by talking about like some energy transfer, basically. So some of the energy is coming from the air, right? So so that would be the specific heat of air times the temperature in, right? So this is coming from the air. And then in addition to that, there's energy from the evaporation of the water. So we're going to have that represented by the enthalpy of vaporization of the water times the pressure of the partial pressure of the water in the air coming in. And we're going to have the molecular weight 2 over RT. And this is something we're ultimately getting from the ideal gas equation. And then we're going to adjust that by the total pressure of the system. So we'll do that, and then a similar like ideal gas equation conversion. So divided by the total pressure times the average molecular weight. And these M's here are just showing molecular weight. So this is the molecular weight of water, and this is the average molecular weight. Now, what we're getting from this right now is, if you look at this, the units right now are joules per kilogram, right? If you just look at this one simply, specific heat is joules per kilogram per Kelvin. We're multiplying by temperature in Kelvin, and so we'll have joules per kilogram. But we want, we don't want this kilogram. We want it to be joules per second because we want like an energy change. So the way we can do that is multiply all this by the mass transfer in the and I should really put dots on these up here. I just realized that would kind of indicate this is a mass flow rate. So yeah, now that we have a mass flow rate in there, I can go ahead and get out my eraser, and we can show that the what am I sorry, I totally lost track. Yeah, because mass transfer is kilograms per second times joules per kilogram. Kilograms are going to cancel, and we'll have this in joules per second. So then the enthalpy out is going to be something similar in structure, but just with different variables. So I'll go ahead and select what we had before. I like that selection. And then I will drag it down here. And so we're going to make a couple changes. Now we need to have the temperature out right here. We don't want the partial pressure. Now the partial pressure of the water in the air is the saturation pressure, so I'll have to change that. And besides that, I think everything should be good. So let me make those changes real quick. We want the T out, and we want the saturation pressure of water at a certain temperature, at the temperature in the problem. So now we have this, we can just set these two sides equal to each other, right? So we'll go ahead and grab side 1. All right. Forgot the hotkey I was supposed to use. It's like, wait, what? What is the hotkey? I forget. Okay. So I'll shrink that down a little bit just to make it fit in a little bit easier. And then we'll go ahead and drag this part down too, and we'll copy paste that. And I'll go ahead and make a couple of small changes just to kind of fix some of the letters. Put an equal sign in there, so we'll erase some of this too, just to get look a little bit nicer. And yeah, so how can we cancel out some of these terms? Well, first thing we can do, cancel the masses, right? And so I said I don't think anything else can. Well, of course, we can cancel these RTs. The gas constant times the temperature. Those will cancel out because it's the same temperature, same gas constant. So now we need to start to kind of combine these terms, and hopefully we should end up with something that looks a lot like this wet bulb temperature equation up in red. So let's just go ahead and say that, let's go ahead and combine the temperature times specific heat terms. So, yeah, and I'm doing this, it's going to give me basically sort of a negative version of what we were doing before, but that's okay. I can just show that a little bit later. So that's why I paused and had to think about it for a second. I think I'm doing this a little bit in reverse. But anyway, we have we brought these temperature in and out together. So the difference in temperature times the specific heat capacity, and then that is going to be equivalent to this lambda. And lambda is the heat of vaporization, the enthalpy of vaporization, rather. And then I'm going to pull out the... ooh, that was so bad. I'm going to pull out the molecular weight and the average molecular weight, or the molecular weight of water and the average molecular weight. And I'm going to combine the like terms so that we have the partial pressure of water over the P total. And that's going to be the partial pressure of water minus the saturation pressure of water at a specific temperature. So we can bring this P total over, and I'm just going to copy paste that, I think. This isn't going to go well. Where should I put this? I'll try to get a lot closer. Now we can maybe fit it in. Yeah, so now that kind of fits in over there. So we got the P total over there, times the specific heat capacity, times the Tn times the temperature difference is going to be equivalent to the heat enthalpy of vaporization times some molecular weight conversions, and that's going to equal the partial pressure of water times the saturation pressure of water at a certain T. So let's go ahead and copy this down real quick. And, actually I didn't want to do that. I'll just copy paste it. That's what I wanted to do, probably. Yeah. So as you can see, there are a lot of similarities between these equations, but there's a few things you might notice that are different. First off, you see, like, sort of the structure, and these terms are kind of flipped around, so it might be better to rearrange these. But just for the sake of time, I won't rearrange. I'll just leave them how they are. You see the pressure total times the Cp times the temperature difference. Now, how do these temperature differences relate? Well, T infinity, that's the temperature far away from the air. That's the temperature that isn't saturated at all. So that would be similar to T in. But temperature at the surface, that temperature is going to be pretty saturated. So that, or at least the water there is going to be saturated. So that would be more like T out. Now, the partial pressure of water, the partial pressure of water going in, which isn't, or we'll start at the saturation pressure. The saturation pressure is going to be similar to this partial pressure over here, and this pressure is, of course, just going to go along with that. So now the only weird thing we have left is the molecular weight of water over the average molecular weight. Now that is, that is kind of weird, because, like, how is that left in here? Well, in part 2, when we solved the problem, we assumed we were given the specific enthalpy in terms of joules per kilogram. Now, in this problem, we were given it, we assumed it was in terms of joules per mole. So we had to use the molecular weight, which is moles per kilogram, or it could be any sort of moles per any mass. I'm just saying kilogram because it's easiest to just go with kilogram to just convert. So that's how those molecular weights ended up staying in there. There's kind of a ratio between them. They'll cancel out unit-wise. And, that's how, part 2, the wet bulb temperature relates to the adiabatic saturation temperature. So this is part B1. And we're going to derive the differential equations for the mole fraction of water vapor in air and the temperature of the air and water in the cooling tower. So if you take a look at this drawing I have over here, you'll see that this is visualizing a cooling tower. And what a cooling tower does is it, or at least what this cooling tower is doing, is it's taking in water and using that water to, and using air to cool water down. So it has a constant gas flow rate, as you can see right here, and a constant liquid flow rate, the liquid being water, the gas being air. And the way we're defining the height of the cooling tower, which is the primary way that the height is the primary way that, like, the concentrations of the gas and liquids are going to vary. So we're defining that as basically going downwards, kind of in the opposite direction of how you would normally define height, because that is how the concentrations of the liquid are changing. So you'll see there's some, like, highs and lows. That's just to show, like, the gas starts at a high temperature down here and goes to a low temperature up here, and that the water starts at a high temperature up here and goes to a low temperature down here. So we're trying to find the changing concentration of water, or mole fraction of water, rather. That's what this Y means. That's mole fraction of water. So it might be better to say H2O, but we're not finding the concentration of air, so it doesn't really matter. And the change in the temperature of the water over time, or not over time, nothing here is over time. A change in or the temperature of the water over the Z, and the change in gas over the Z. So let's go ahead and think about this for a second. So we have gas flowing in from the top, and by the way, this gas flow rate, it's not just kilograms per second, it's not just a mass flow rate, it is actually, and the liquid is the same way, it is a gas flow rate per area. And that's just going to let us cancel out some units later on. So that's kind of why we're doing that. So let's just start out by setting up an mass balance to solve for this first equation, right? So we're trying to solve a mass balance. That's what that means. So first things first, let's find the differential of the gas flow rate. Sorry, there's some dogs in the background. They're being kind of silly. I don't know. They keep moving and it's distracting me, so that's why I just looked over there. There's this gas flow rate, and the gas flow rate, we have to multiply it by the surface area. So this A means the surface area of the kind of porous mixture that is yeah. So this A means the surface area. Now also, another thing to note about this column is that it has a specific area, and that's going to be the surface area per volume. So you could put that as meters squared per meters cubed, and that's going to be like a little a. I wrote an alpha there. Maybe I should try to turn that into an a. Yeah, now it's an a. So those are two important factors I forgot to go over. So we're going to look at the change in this flow rate multiplied by the molecular weight. And we're also going to multiply that and look at the change in the mole fraction of water. So we'll go ahead and that'll be one side of our mass balance. And the other side of the mass balance, well, we know that the change in concentration is driven by diffusion, right? So we could, or it's not driven, it's just driven by a concentration difference. So we can talk about it in terms of a mass transfer coefficient is equivalent to a difference in concentration. Now, this difference in concentration, we need to adjust it for the surface area. So we're going to take the specific area times the volumetric times the surface area, and then we're looking at that as z changes as we go up or down the cooling tower. So yeah, with that all in mind, let's see if some things don't cancel out a little bit. So first off, let's talk about what we're taking the differential of on this side. The gas flow rate is constant. There's the same flow in as there is out. So the gas flow rate is constant here. And how does my camera look? I'm in the shot. Okay. Sorry, I had to check and make sure I was in the shot pretty good. Yeah, so, yeah, so the gas flow rate is going to be constant. The area is going to be constant, and the molecular weight is going to be constant. Now, this area is even going to cancel, so I can cancel those out, and we're just going to be left with the change in concentration. I'm going to divide over this dz because this is ultimately what we're looking for. This change in concentration over change in z is going to be equivalent to the molar, it's nothing molar, the molecular weight. Kind of similar sounds, so I can't hold me liable for that one. Times the specific area. And then we're going to multiply that by, or that would be negative as well. We're going to multiply that by Kc times, real quick, let me change this concentration difference a little bit. Instead of talking about the concentration difference, I believe we're going to be given some partial pressures. So we should use the ideal gas equation to change this around. So we know concentration turns into P over RT. So this concentration at the surface, that's kind of the interface between the water and they're starting to, I hope they don't fight over there. I don't know. They might fight each other. Who knows? Where's my cursor? There it is. So we know that that's actually going to be the saturated pressure of the water. So that's saturated pressure of the water in the air at a temperature. Now that's going to be subtracted by the concentration at infinity, which is far away from where the diffusion is taking place, which would be the partial pressure of water in the air. But that partial pressure of water in the air is actually going to be something a little bit different. We could write that as the mole fraction of water in the air times the total pressure. because that's the definition of partial pressures, right? So, and they're really, I don't know. I'm upset they're fighting because I just want to do my homework and the dogs are fighting. So I'm not a huge fan of that one, not gonna lie. Anyway, so now that we've got this written out, you might notice something if you condense all these units, and this is that this right here is actually molar flux. So we could go ahead and write that as the molar flux of water, and we could say that the change in concentration of water over the change in distance. Hey! Be nice. I'm not going to pet you. You're being bad. Now they're going to get under my feet and be annoying. That's fun. Yeah. So that's the molecular weight times the... Sorry, I can't believe I'm just blanking on that right now. Times the specific area divided by the gas flow rate. And let me move in this molar flux of water a little bit closer just for the final take. So then I'll go ahead and select that and copy paste it. And yeah, look at that. So now we have equation 1. Now equation 2, we're looking for the change in temperature of the water over the change in Z, over the change in height. So yeah, let's go ahead and get 2. Now, because this is because this is like a cooling tower, and we're looking for a change in temperature, let's go ahead and set up and let's go ahead and set up it like an enthalpy balance, right? So I'll write that as HBAL. And HBAL, and this is for water, because once again, we're just looking at the temperature of water right here. So we have this HBAL of water, and what are we going to do? Well, we'll say that the change in enthalpy of water is going to be equivalent to the liquid flow rate, because water is the liquid, times the specific heat of the liquid or water. And remember, this is how we get enthalpy. We use something similar in the last problem. Now we're going to have to multiply that by the area, right? Because we need to, this liquid flow rate is given to us with this meter squared. We just want kilograms per second. And then we're going to need to multiply that by a change in temperature. So we're going to look at like how temperature of water. Yeah, temperature of water. That's what we're going for. Yeah, exactly. So what is that going to be equivalent to? Well, that's going to be equivalent to, well, first off, we would need the heat transfer and then the evaporation, the enthalpy from evaporation. So we could go ahead and write heat transfer because it's occurring because of a temperature difference between the water and the air. So that would be the temperature of the... I think it would be the gas, right? Because the gas is higher than the... well, I think it's the gas minus the water. So that temperature difference, and then that temperature difference we're going to need to adjust by the surface area and the volume. And then that's also going to be, we're going to need to take away the evaporation energy. We're going to need to subtract that out. So we're going to take the heat of vaporization times, the heat of vaporization times the molar flux, right? Because we're looking at how fast it's diffusing, times, and once again, we need to adjust for that again. So going to grab that, and and then all of this is actually going to be changing with respect to z. So I'll go ahead and just maybe put a big dz. Right. So yeah. Okay, they're being good now, so I'm glad about that. Yeah. So now that we have all this stuff, let's go ahead and try to cancel out some of these units. So first off, the surface areas cancel, right? So boom, boom, boom. we can divide over this dz to get what we're looking for, and then we can divide over the liquid flow rate times the specific heat of the liquid. So let's just do that. I'll copy this, divide it by this, and we'll set that equal to 1 over that. I like using the copy paste stuff. I feel like it's a lot more fun for me to use that. I like that parenthesis. That's a good parenthesis. That's another good parenthesis. Sometimes your parentheses look a lot like C's, and it's a little bit hard to tell them apart. So I'm glad I can kind of get that under control. And then we'll take out an A out of here, because you notice there's a little a. There's a sorry, I shouldn't say little a. I should say that this is the specific area, or the area per volume. And then we're just going to subtract the specific heat and the molar flux still. So you do that, and yeah, this is such an ugly A. Let me fix this one up real quick. A, it looks like a Q now. I don't know why I'm getting hung up on this. There's an A. Look at that. So with all this, now we have an equation that relates the change in temperature of the water to the change in height. So we'll just copy paste that, and we will bring it up here. I like that. So now that we've done that, let's go ahead and let's take a look at part 3. So part 3, we're looking at the change in gas over the change in height. So we could do something kind of similar to what we did with the change in temperature of the water, but we can actually probably simplify it a little bit and do this a little bit quicker. So what we're going to do is, instead of just setting up an enthalpy balance for the water, we're going to set up an enthalpy balance for the whole system. Now, I know you're thinking, how can we do that, right? Well, if you recall, this is a steady state process. Right, this is occurring at a steady state, water and we'll say gas. So this is a steady state process, which means that the change in enthalpy, and I'm going to type this out actually because I think it'll go a lot faster. I'm going to redo that and type. So steady state means there is steady state means there's no net change in enthalpy. Now, because there's no net change in enthalpy, we know that the change in enthalpy of the water is going to equal the change in enthalpy of the gas. So that's pretty good. That's going to allow us to figure some stuff out. And Paint is so poorly designed in some ways. Like, things will just randomly get cut off. Like, what even is that, you know? But I don't know. I shouldn't complain. I couldn't do it if I tried. So, yeah. So we already have the change in enthalpy of the water. So we'll leave that alone for now. But how do we get the change in enthalpy of the gas? Well, let's set up something kind of similar to what we just did. But the change in enthalpy of the gas should be a little bit more simple to derive. So once again, we're going to have to go with the gas flow rate. This is just the enthalpy from the gas itself, the vapor, or just the gas. I shouldn't say the vapor, because the vapor would be referring to the water. And we're going to have to adjust that by the A, and then multiply that by the TG, the gas temperature, and we are going to take the difference of that. Well, shoot, we're going to take the difference of the whole thing, right? Yeah. So we're going to take the difference of the whole thing, actually. So let me just keep that differential over there, and we're going to actually subtract out the heat of vaporization of the gas times the gas. We got to adjust this gas flow rate for the area, because the gas flow rate is per area, and then divide that by the molecular weight, and multiply that by the mole fraction. So that way we're finding the amount of enthalpy that is coming from the goal, or is coming from the molar transfer. How much time have I used? 17 minutes, that's okay. So now with this, we can go ahead and just select that, if I can. I should do. So we're going to select that, and yeah, we could simplify it a little bit, but for now we'll just set that equal to what we just did over here in part 2, or in like the second problem I solved, which is yeah. So we'll just set that equal to the change in enthalpy of the water. Yeah. Now that we have this, we can go ahead and simplify it a little bit. So out of this whole first term that we are taking the derivative of, essentially, the only one that's changing over time is the temperature of the gas. So we'll have the change in temperature of the gas times and then all these A's are going to cancel, right? That's something we've always been doing. And then I'm going to divide this dz over already. So this change in temperature of the gas times the gas flow rate times the specific enthalpy of gas, and then minus, well, this heat of vaporization, that's a set value. The gas flow rate is constant. The area cancels out. The molecular weight is constant, but this change in water's mole fraction, well, we solved this earlier. So we see there's a dy there over dz, because we're dividing over the dz, the change in height, and then we're going to multiply that by the heat of vaporization, the g, and the molecular weight. So yeah, with that in mind, we can kind of just copy paste. There's not necessarily a whole lot of reduction to be done on this side. So yeah, I'll just go ahead and bring that down. Equal, and then I might erase some things for just a second to make sure that like everything looks good. We don't need those A's anymore. We could factor out the specific area, but I'll do that later, because there's something important that we can do right now. And yeah, let's take a look at that real quick. So the specific area A, no, that's not what we're focusing on. So if you look at this second term right here, this is the lambda times the molar flux times the specific area. Well, if you look over here, we have this dy over dz. Well, up here, we know what dy over dz is, right? So, yeah, look at that. So I'm going to shrink this down a little bit just so it's not taking up a bunch of space. But you see there's a negative molecular weight times the gas flow rate. So those will cancel each other out right here. And it's negative. So it should move that up. Actually, no, shoot, this is supposed to be added on there. And this negative is supposed to, this negative is supposed to make it negative. So this should be positive. I believe. Because basically, this term, not that term, this term right here is going to cancel out this term right here. So I'm just going to put big crosses through both those, and that should make things a little bit more simple. So now we'll isolate what we're looking for, the change in temperature over the change in height. So the change in temperature over the change in height is going to equal the heat transfer coefficient times the specific area over the gas flow rate times the specific enthalpy of the gas. And then that's going to be multiplied by the change in, or the temperature difference between the gas and the water. So, yeah, I'm going to save that. I'm going to make sure it's saved because, I don't know, didn't feel like it's saved there. And, yeah, with that, we're pretty much wrapped up with these equations. So what we're going to be able to do in the next part that's so important is we're going to be able to use Python to solve out these given specific values, and we're going to use a root solver to kind of like discern, get to the bottom of what's going on. And yeah, so that all looks good, and yeah, let's go on to the next part. So now on to part B2. Solve the differential equations derived in B1 for a 20-meter tall cooling tower where the air-water heat transfer coefficient is 10 watts per meters squared Kelvin. There should be a division there. Sorry, the paper was flapping around over there. The specific area of there, the hot water enters at a certain temperature with a flow rate of 0.5 kilograms per meter squared per second. So that's a volumetric, or yeah, that's a mass flow rate, so we like that one. But air enters from the bottom with a velocity of 5 meters per second. That's not quite as helpful, right? That's going to be a little bit more annoying to work with. That's not really what we want, so we're going to have to convert that around. And at a temperature and relative humidity of 25 degrees Celsius and 50% respectively, make plots of the water temperature, air temperature, and the water partial pressure as a function of position in the cooling tower. Okay. So let's go to this file, and I'll talk through some of this. So first we import some functions. NumPy is short for numerical Python. We're going to use some linspace functions from it. We're going to use the subplots, these two things, to make some plots. And we're changing the template to dark just so it looks a little bit more appealing. And from the integrate library, we're going to import solve IVP. This is a function that we're going to use to solve the initial value problem for like basically finding, kind of similar to optimizing, which is finding like the zeros of a function. So first things first, I brought in this Antoine equation. If we look right here, it's just a Wikipedia page on the Antoine equation. What's a good depiction of it? There's some extensions down there, but the bulk of the Antoine equation is right here. So the log 10 of the pressure equals some constants that relate the temperature to the pressure. So what the Antoine equation gives us is the vapor pressure at a certain temperature. And so I just brought in those and all the different constants. And then at the end, I converted it to pascals. So that's what this is doing back here at the end. So then we'll go through some of the constants. Most of these are either given or things we're going to need to reference. So we have the heat transfer coefficient, the gas constant, density of the air, the specific heat of the air, the specific heat of the water as a gas, the specific heat of the water as a liquid, the heat of vaporization, the mass transfer coefficient, which is just basically derived from here. You can see, this is kind of a breakdown of what the mass transfer coefficient is. That's how we got there. And then, we have this A value. That's the, remember, the specific area. So it's meters, it's area per volume, surface area per volume. The molecular weight of water, which is in kilograms per mole. So that's why we're multiplying it by, we're dividing it by 1,000. Similarly for air. Then the velocity, which was given to us, the liquid flow rate, which was given to us, and the basic pressure, which we're just assuming is 1 atm or that many pascals. So with that in mind, let's go ahead and keep going. So we know the height of the cooling tower is going to equal 20. So we'll put that in. And then on top of that, let's go ahead and bring in this Z plot. I'll capitalize it. Yeah. So the Z plot is going to be, we're going to use this NumPy linspace function that's just going to give us some linearly spaced out values. And we're going to use that for plotting later, but I'll go ahead and put that in now. So we're just going to start at 0 and go to the end of Z. The end of Z is going to be at height. And the number of points, let's give it 21 points, so that way it breaks them up nice and evenly from 0 all the way to 20. So that should be all good. Now we will put in the temperature of water in the feed. I'll capitalize feed. So the temperature of water in the feed is going to be hot water enters the top at 70 degrees Celsius. So that's going to be 70. I wrote that wrong. And we're going to add 273 to turn it into Kelvin. And then similarly with the gas feed temperature is going to be, or the air, it's not, yeah. And we'll have the relative humidity in a second, with 25 degrees Celsius and 50% respectively. So the temperature of the air in the feed is going to be, the temperature of the air in the feed is going to be, what did I just read? I forgot. 25 degrees Celsius. So 25 degrees Celsius plus 273, once again, to convert it to Kelvin. So now we need to get the mole fraction. Actually, real quick, before we even do that, let's bring in this relative humidity. So I'll just abbreviate that as RH is going to be 0.5. It's given to us 50%, 50%, 0.5, same thing. So how do we find the YA feed? Well, I think if you recall, if we go back a little bit, let's see, where is it? We talked about, is it right here? Not quite. Right here. Yeah, okay. So we defined relative humidity as the saturation, or as the partial pressure of water over the saturation pressure of water. So remember, the partial pressure of water is actually equivalent to the mole fraction of water times the total pressure, right? So with that in mind, we can solve for the mole fraction of water, and if we know the total pressure, the saturation pressure, and the relative humidity, which we of course do. So yeah, let's see. So actually, I'm going to keep that one up. I like that one. Yeah. So I'm going to go ahead and bring this over to the side. And let's see, YA of feed is going to be equivalent to the relative humidity times the saturation pressure. So that's going to be from the PV table at a certain temperature, at the temperature of the gas in. So at this TA feed. And once again, when I say gas, I mean air. I just keep misspeaking. And then that's going to be divided by the P total, I believe. So, yeah. PV is not defined. Have I not run this? Oh, it's P lowercase v. My bad. Yeah. Okay. Well, that looks good. So continuing on, we need to find the gas flow rate in terms of like a mass flow rate. So we want kilograms per meter squared per second. So we know that the gas flow, we're given the velocity, of course, but the velocity isn't very, it's not really the way so we have to convert the velocity to something else. So we'll multiply this velocity by the partial pressure of the air. Actually, no. What am I talking about? We're going to multiply it by the total pressure of the air times the molecular weight of the air, and then divide that by the gas constant times the feed temperature of the air. I thought that would go better. Yeah. And this is just to using the ideal gas equation to convert the velocity to the gas pressure, or to the mass flow rate. So now we need to get some guesses. So we're we're eventually going to use this root solver, and the root solver is going to actually end up needing like a guess for the Y exit. So for the mole fraction of the water in the exit, then it's also going to need a TG, or the temperature of the gas exit estimate. So we'll define these both as guesses. ESS, I can't spell. And we're going to set this one equal to, we will set it equal to, the concentration of air in the feed. We'll just multiply it by 1.1. This is just from kind of an estimate. And then the TG exit, we'll take the temperature of the air in the feed and multiply that by we'll multiply. We'll add say 5 to it. So with that all good, we can go ahead and do this. We can define a function. So we are going to go ahead and define a function that basically goes from the lowest temperature. No, what am I talking about? We're basically defining, you see how we have these three functions over here and they're all relative to dz? Well, we can define one function with three parameters, and one parameter is going to be the change in mole fraction, one's the change in water temperature, one's the change in gas temperature. So that's how we're going to do this. So we'll define the function, and we'll call the function dy dtg. I don't like that. Dtg and dtw, just for the different, and I'll switch around the. Sorry, I just need to focus on what I was doing there for a second. And we're going to define it in terms of z as the independent variable. So the z is what we're altering as we go down. And the dependent variable, we're just going to call v, because v is kind of a placeholder. We're having multiple variables represented by v. So the first sort of term in this v, or the first part of v, we're going to define y, or the mole fraction of water, as equivalent to V0. And then in the second term, that being Tg, actually we'll say Tw just to stick with the same order. The temperature of the water is going to be the second term of that V. So then the third term is going to be the temperature in the gas phase. So, yeah. So looks good. So now we need to define the gas flow rate for the water. So this is for the water vapor, essentially, you could say. So this is the water within the gas. So that's going to be defined as the ratio between the two components' mole fractions. So y is the amount of water, the mole fraction of water, times the divided by the 1 minus y, which would be the mole fraction of the air in the air. And by air in the air, I mean the dry air in the air, I think is a better way to explain that. So then we can take that and we multiply that by the MW, or yeah, the mole, or the mass, molar mass of the water divided by the molar mass of the air. So then we're just going to really quickly define the total gas flow rate as GW, gas flow rate of the water plus the gas flow rate of the air. And it did everything wrong. Why? Are you kidding me? So annoying. Yeah. So now we need to define the total molecular weight. The total molecular weight can be defined as the G, or this total gas, divided by the gas flow rate in the air times the specific heat of the air plus the gas flow rate of the water multiplied by the specific heat of the water. You know what? I am totally screwing that up right now, right? Because if you look up here, that yeah, I should be dividing this by the molecular weight. So I'm really trying to find the gas flow rates are telling me almost like what the mole fraction is of the of the water and the air in the air. So I should really be dividing each one by the mole fraction. So that's my bad. I had to take a look at that for a second and think about it. So then with that, we can go on down, and now we want to find the concentration of, sorry, I don't know why I just said concentration, the specific heat of the gas. And that's just going to be based on how much bone dry air there is in the air, and how much water there is in the air. So we can just say the sea air times the gas flow rate of the air plus the sea water, specific heat of the water, times the specific heat of the water, and then we got to divide that by the total gas flow rate. No, why does it? I'm hitting enter, not tab. That's just annoying. So I'm gonna save this real quick. Does this automatically save like Google Drives do? I'm not sure because it says it saves, so I don't think it does. But anyway, now it's time for us to start importing these functions, finally, after a lot of preparatory work. So first things first, let's define NW, or the molar flux, because so if you look down here, and I'm trying to see where exactly it is on the document, but where did I put that? Where did I put that? Oh, okay, here it is. So molar flux can be defined as Kc times, and I know this is wrong, and we'll divide that by R and divide it by some temperature, and I'll elaborate on what that temperature is in a second. We have to multiply it by the saturation temperature, the saturation pressure. So we can get that from Antoine, right? So we get that from PV. So from PV at a certain temperature, which is the same temperature as before, minus the mole fraction, which we've already defined, times the total pressure, which we've already defined right here. But what is this temperature exactly for the molar flux? Well, if you look at it, it's going to be the saturation temperature of the water. Or it's going to be the temperature at which the water is separated at a certain T. It's the temperature of the water. And it's actually going to be, this TW right here. So the TW is going to go right there, and it's going to go right there. So, now that we can go down once again, and now we'll go back up here, and now let's put in an equation for the change in mole fraction of water. So the change in mole fraction of water is going to be for the average molecular weight of water times that specific, a specific volume of A, and divided by the total gas flow rate multiplied by the molar flux. Then the change in temperature of water is defined as the specific volume of water divided by L, the liquid flow rate, which I think I actually defined that a little bit differently up here. Actually, no, it is just L. Okay, so that variable was correct, and then divided again by the specific heat of the water as a liquid. So that's that. We'll pull that variable down. And then we're going to multiply it by this temperature difference times a heat transfer coefficient subtracted by these heat vaporization times the molecular weight. So, that's going to be H times Tg minus Tw minus the heat of vaporization times the molecular weight of water. So that's awesome. Am I recording still? Yes, I am. Right? Yeah, okay. I just always get freaked out that I'm not recording. I've never had an issue with that. I don't know, it just always alarms me. So then the change in so the change in the temperature of the gas, that's what I'm looking for next. That's the last formula we have down here. So that's going to be the heat transfer coefficient times the specific heat divided by the total gas flow rate divided by the specific heat of the gas. So that would be the specific heat of the air right here. Actually, no, it wouldn't. It would be the CG right here because this is like the average specific heat of the gas. So then we're going to multiply that by the temperature of the gas minus the temperature of the water. And yeah, that's good. So then this function needs to return something. And this function is actually, we're going to have it return the dy, the change in water temperature, and the change in temperature of the gas. So if we were to go ahead and run this, it wouldn't give us any errors, but also wouldn't give us any results. And that's because it doesn't really know what length to evaluate this for. So let's go ahead and tab this over and move it down a couple. And we'll define another function around this function. So this function we'll call convergence. Convergence of the temperature of the air with the molar. Actually, you know what? We'll just call it convergence, and we'll leave it at that. And this just is going to have a couple of like placeholder variables that we don't really need to call, so we'll just call them v2. And yeah, so the y. Yeah, so we need to basically define the variables of this converged feed air temperature function. We need to define the variables as kind of like the intervals of this of this function, the change in the y, change in temperature of the water, etc. And then we're going to set the sol equal to global, or we're going to set sol as like a global variable so it can be accessed at any point inside or outside of the function. And in that break, I went through and checked a bunch of the variables. I found that a couple things were probably running correctly. There's supposed to be a negative sign on this dy, which I should have known, but I just forgot about. So yeah, with that all in mind, let's go ahead and keep going. So right here, we're going to define sol, and we're going to define sol as the solve of the initial value problem, solving the initial value problem of what function? Well, this function, and then we need a time span. So that time span is going to be from 0 to the height of the container, which would be 20. Then the initial conditions. So the initial conditions of this are going to be this y exit, right? And then it's going to be the temperature of the air in the feed. The temperature of the air in the feed, because the air comes in at the top, and we're defining the top. Actually, let me visualize this for a second. We're defining the top of the cooling tower as z equals 0. So the initial condition would be that, and then and then the final condition would be this temperature of the gas exit. You know what? I think when I said I meant the temperature of the water in the feed, I believe, not the temperature of the air. Because if you look at this chart, the temperature of the water in is going to be the so then with that, what else? We'll give it the method is going to be Radu. That just gives the best results. Time evaluation, we're just going to do dense output equals true. I didn't capitalize it. I didn't capitalize it again. And then we're going to solve it for the values at z. And then we're going to solve at the values of z plot. So those are like our values going from 0 to 20. And how how do I show up if I'm like this to this? Okay, I show up pretty well. Now we need to return something from, if I could spell it, return something from this conversions feed air temperature. We're going to return, we're going to return sol, the first value, or we're going to, the first value in the array, and then the last value, and we got to subtract that from the, that would be the mole fraction of air in the feed. And then additionally, we need to take the third value of that array and the last, or the third array and the last value of the array. And we need to subtract out, the TA of the feed. So when we go ahead and, I feel like I'm forgetting something, that's why I gotta think. I guess we can just go ahead and run it and see what happens. So now we're going to use a root function. So the root of the function, that would be this converge feed air temperature. Then the initial guesses, this x0, the initial guesses we did up here. So it's going to be the y exit guess and the TG exit guess. And then, I think that's all we need for root. So if we go ahead and run that, then, the numbers we get look about right. So let's go ahead and plot this out a little bit. So first off, we'll define a figure as make subplots, and it is going to have 3 rows and 1 column. So we go on down and we take fig and we add a scatter, wants a bunch of different information. We just need to give it an x value, a y value, and we could give it a label, maybe even. We'll leave that down. We'll leave that away for now. So the x values of this, well, those are just going to come from z plot, right? And z plot, if you if you look up here, where's z plot at? Where did I put that? Yeah, here it is. So that's just the linearly spaced values from 0 to the height, and there's 21 of them, so it's just 0, 1, 2, 3, 4, 5, 6, yada, yada, yada. So the y value is going to be sol, and it is going to be, for this first one, we'll do the mole fraction, so that's going to be the first array in sol, the 0th array, you could say. And then we're going to use a colon to show we want all the values of that array. And let's just go ahead and plot it and see what we get. Ooh, we didn't like that. Probably because I put in the wrong thing for z-plot. I don't think... I didn't want to do that. Delete cell. So this is what we would expect, right? At the top of the cooling tower. Let me go back. Right. At the top of the cooling tower, you see that the mole fraction of the water in the air is high, and then it gets lower as you go down the cooling tower because the water is evaporating. The liquid water is evaporating into the air, right? So additionally, sorry, I thought like a dog or something was coming to visit me. We can do something similar for these other two. So we'll do something similar for the first column and for the second. We'll go ahead and plot those out. Shoot, these are all in the same graph. Well, let's go ahead and change that real quick. So we'll set this one equal to row 1 and column equal to 1. And we'll go ahead and give it a name. And the name we'll give this one is Y H2O. And yeah, separate that with a comma. And we can run this again. And it should do the same thing, but we should be able to fix it a little bit. Yeah. So the second column, well, the second value in our array is going to be, and let's go back a little bit. The second value in the array is going to be the change in temperature of the water. So we'll call that TW. And then that's going to go in row 2 of column 1. And then okay, what I did wasn't that bad. So we'll just copy that over again. And now it's going to be the temperature of the gas in row 3. So we go ahead and run that. And yeah, look at that. So what these charts are saying is that the temperature of the water at the top of the column starts out at a higher temperature, and as you go down the column, the temperature gets lower, which makes sense because the water is being cooled. And then the temperature of the gas down here, it starts out high at the top of the column, but as you go down the column, the gas cools as well. And that's because the gas is moving in the opposite direction of the water. So the gas is starting out cooler and heating up as it goes up in the column. So that's why like the temperatures kind of follow the same trend line. So that's about all I have for this. Thanks for watching. I hope you learned something. I certainly did. And yeah, have a nice one. Bye-bye.